Here we discuss how we can write mass conservation for internal flows. And when I talk about internal flows, think the flow through a pipe, a nozzle, or a microfluidic channel, for example. Essentially, any flow where the flow is inside a structure. Right, so think about here, that could be a pipe, and the flow is inside of a solid structure. So let's say that we have our x-axis is our main axis of flow. Oh, sorry, I have to put the y-axis this way. So say we have this structure here, and we have this internal flow. Right, so whenever you can easily recognize an internal flow because you essentially can define an inlet and an outlet. So flow is flowing in from one side and flowing out from the other side. So how does the mass conservation statement looks like for such an internal flow? And we'll assume on top of that the flow is steady. So let's assume a steady flow. So before we write our mass conservation statement, we have to choose a good control volume, and in that case, for an internal flow, a control volume, an appropriate control volume is rather trivial to define, right? What you want to take is as a control volume, and if the fluid, all of the fluid which is actually inside of this channel. So we have we have this control volume here, right? That would be our control volume. And if we look at the control surface really has three parts. You would have here an inlet. We have here the outlet, and the last part is the side surface, right? The one that really touches the solid. Right? All three together form the control surface. You cannot leave one. You cannot leave one out. So now we can write for this particular control volume our statement of mass conservation. And because the flow is steady means that nothing changes with time, then we know that this term is equal to 0 because the flow is steady. And so we are left with this part here of the flux part, which has to be equal to 0. So the net mass flow rate coming out of the control surface has to be equal to 0. Now this one has three components. It has the integral over the inlet, the integral over the outlet, and the integral over the side surface. So the sum of these three terms has to be equal to 0. Now what are these terms equal to? Let's look at the outlet. So here is our outlet. The velocity field coming out of the outlet is, so the velocity field here at the outlet is going to be u at x equals x outlet, y z. It's independent of time because it's steady. Same for v at x equals x outlet, y z. I'm writing this dependency here, but usually I will omit. Right. And what is the normal vector on the outlet? Right, so here, I didn't say before, but we pick our surface here to have a normal, to be normal to x. Right, so our normal vector on the outlet is pointing to the right. So the coordinates of n are 1, 0, 0. So this is dot 1, 0, 0. Likewise, on the inlet, we have our velocity vector, which has in the x component the velocity at x inlet, y, z, v at x inlet, y, z in the y direction, and in the z direction, x at x equals inlet, y, z. Right, for clarity, here the inlet is at x equals x in, this is what I mean, and the outlet is at x equals x outlet. Alright, so at the inlet, remember that the normal vector is always pointing outside of the control volume, so our normal vector here is pointing to the left. Right, so the components of the normal vector for the inlet are -1, 0, 0. And now, what about our last surface, which is the side here? What is the mass, the net mass flow rate through the side? Clearly, it is equal to 0, and that we'll discuss later. It's because of mass conservation, but we don't have any air or any fluid leaving the control volume to go into the solid. That's just not possible physically. So we know that this part here is equal to 0 because there is no mass flow through a solid surface, through a fluid-solid interface. Okay, so this dot product here is clearly equal to u at x out, y, z, and this one here is equal to minus u at x in, y, and z, and therefore we are left with the integral over the inlet of minus rho u, and u is really the x component of the velocity vector, so at x equals x in, y, z times ds plus the integral over the outlet of rho u at x outlet, y, and z ds. And that is equal to 0. Another way of writing this is simply that the mass flow rate through the inlet, because there is a minus sign here, right, so the mass flow rate through the inlet, now this is not a vector, I want to be careful here, this is the x component of the velocity field at x in, y, z ds is equal to the mass flow rate coming out of the outlet, so rho u at x out, y, z ds. This is one way of writing mass conservation. Clearly, we randomly pick our control volume. We could have picked it a little bit, this x in and this x out we picked a little bit randomly. We could also write mass conservation by just saying that the integral over any cross-section A at any given x of rho u x y z ds is equal to a constant. Right, so our mass flow rate through any cross section of our pipe, for instance, is a constant. This is a statement of mass conservation for an internal flow.